Right, so this is Tri-band Tribulations. The words probably don't make an awful lot of sense, and I will explain what I mean by tri-band in just a few slides' time. But it's all about imaging objects in the universe, perhaps nebula, perhaps stars, in a way that gets around some of the light pollution that we see in the UK. So I'll be talking about colour imaging and colour cameras briefly to give a little bit of context, and then talk about the nature of the light that's coming from astronomical objects, light from stars and nebula. That's the light we're trying to catch, but then there's always light that gets in the way, the light from sodium or mercury or, these days, LED streetlights. And then I'll be talking about these things, filters that can be used for astrophotography to try and get rid of light pollution. There are lots of different types of filters, and I'll be looking at color transmission through those filters. And then just to show you what these filters can do, I'll take one example of a filtered and unfiltered image to hopefully convince you that in some cases using filters for astrophotography can be valuable. So firstly, just a little bit of context. How does a digital camera take color images? And not necessarily talking about digital SLR cameras, it's effectively any camera that takes color images. Some people buy themselves astro cameras that are specifically for astronomy, and these might be labeled OSC, one-shot color, because they work the same way as the cameras in your phone. They take a single image which comes out as color. If you're using mono cameras and you want to take a color image, you have to effectively take 3 images, an image with a blue filter, an image with a green filter, an image with a red filter, and then combine them together to get a color image. So I'm talking about color cameras or one-shot color cameras in the astronomical sense. And they pretty much work in the same way, regardless of what box they come in. The actual CCD chip in the camera has effectively, rather than filters that are external to the camera, the filters are actually built into the chip. If you blow up the surface of the chip, every single pixel on the chip, all 20 million of them or whatever it is, will have a small colored filter on the front of the pixel. So you will end up with some of the pixels registering green light, some blue, some red. And so you can see from the pattern in which those pixels are laid out, you end up with a rather sparse grid of red information, green information, blue information. But essentially, a computer takes care of that inside the camera and merges those 3 into a color image. Now, the camera's sensitivity is usually something like this. The filtering of the colors in the camera will be such that it lets through a range of blue, a range of green, and a range of red. And they overlap so you don't get any artifacts at wavelengths that correspond to the transition from one filter to the next. It wasn't until I started researching this talk that I realized that actually that is quite different from the color response of the human eye. The rods and cones in your eye, which might be described as red, green, and blue cones in your eye, don't have the same color response, but that I think is a completely different talk, so we'll leave that for another day. So, color astrophotography. What we would like to do is to be able to photograph objects in the night sky. So, for instance, I have a Nikon camera, other cameras are available, and I like taking pictures with that camera without using a telescope, and some of those pictures will show some of the beautiful colors that actually exist in nature. Bear in mind that you don't see these colors with your naked eye simply because the color receptors in your eye do not work well at low level. So we have cones that give you the color response, and we have rod cells in the back of the eye which pick up low light but are not sensitive to color. They don't discriminate. So by eye, you would pick up essentially monochrome images. Even in a relatively large telescope collecting a lot of light, you will still barely see any color at all in any of these images, which is a shame because color photography clearly brings out those colors by integrating over many minutes, sometimes hours. You can pick up these wonderful colors. But all astrophotographers, especially those in the UK, are fighting the fact that we have light pollution. You can see just how bright the planet is. Here in Merseyside, we're in a relatively white spot. In other words, even on the Wirral, which is a little bit more countrified, even there's still an awful lot of light spilling over from Birkenhead and Liverpool. And the Ruhr is just crazy. And you can see that if you really wanted to go to dark skies in order to pick up the best astrophotography without any light pollution, you need to go to the Alps or the Pyrenees, or perhaps the middle of Australia, if that's the best place to do it. So if you live somewhere close to light pollution, what can you do in terms of trying to take pictures of the night sky that aren't too heavily affected by this stuff? Not only might you have natural light pollution from functional streetlights, in some cases art also gets in the way. This is not functional, that is a piece of art, but it's producing a whole load more light where you don't really want it. So this gives you an idea of what light pollution might do to your images. The left shows a raw image. So in other words, an image taken by, in this case, a digital SLR camera, basically straight out of the camera, no processing other than take the image which has already had the red, green, blue combined. And it shows a huge amount of light pollution. Even though it was in a relatively dark sky, you look up and the sky might look dark, but when you take an image, because the camera is so much more sensitive than the eye, you start to see far more than you want. And you realize that the entire image is glowing with a bit of orange from local streetlights. Now, software can deal with that. Software these days is amazingly good at taking an image where you think it's very difficult to see that nebula in there with all this light pollution, but software can do a great job, as long as the light pollution isn't too bad, the software can do a great job at pulling out detail. And now you can perhaps see why this particular nebula is called the North America Nebula, because of its outline. And that particular object is glowing from the light from hydrogen clouds and oxygen clouds, and it's giving characteristic colors. So can filters help? If we've got the light we want to collect from the sky and the light we don't want to collect from street lights, is it possible that filters will help us get rid of what we don't want and let through what we do want? So software can do a job, but would it be better to filter the light in the first place to limit how much background light we have? Surely that will give us less noise or better signal to noise and hence better images. So what exactly do different filters do? I checked online to see how many filters are possible to buy that have the job of improving astro images. I found 50 different types of filter. And so I started to think, well, are they all different? What exactly do these filters do? And before we can answer that question, we have to consider the colors of astronomical objects. So there's an awful lot of stars out there. Stars are effectively black bodies. Okay, they're hot, but they still have a black body spectrum. In other words, stars radiate over the entire electromagnetic spectrum. Most stars produce a lot of radiation in the visible part of the spectrum. And galaxies, as far as we're concerned, galaxies are really just a collection of stars. Yes, there's other stuff in there as well, but a galaxy is effectively just a collection of stars, and therefore you would expect the light from these objects to cover the whole of the visible spectrum. Now, individually, red stars would be brighter in the red and darker in the blue, and blue stars would be brighter in the blue and darker in the red. But by the time you've averaged over thousands of stars, or possibly even billions of stars, you would expect most of the visible part of the spectrum to be populated. So as far as we're concerned, it's a continuous spectrum from stars and galaxies. But a cloud of hydrogen, or a cloud of oxygen, and most nebulae that exist, most clouds that exist out there in the Milky Way, are usually made of hydrogen or oxygen or perhaps sulfur. A limited number of different elements make up most of the interstellar medium. These interesting clouds, which might be about to form stars, or they might be stars that have come to the end of their lives and the outer atmosphere of the star has been blown away. But because there are just one or two or three elements in these clouds, in these nebula, and because they are very dilute, the atoms are well separated, not interacting with each other, the spectrum from such an object is effectively a set of atomic spectra. So in other words, from this particular object, we might expect to get a well-defined line corresponding to the emission from hydrogen atoms, and another line that happens to occur in the cyan, which corresponds to the emission of oxygen atoms. So if you remember nothing else from this slide, remember red in hydrogen and cyan for oxygen. If we have those two elements present, we see those two lines in the emission spectrum. What about light pollution? Well, light pollution, unfortunately, is equally complicated in the sense that, again, we get different spectra for different streetlights. Streetlights that we're familiar with in England that come from sodium give a characteristic yellowy orange glow because there's a very bright yellow line in a sodium spectrum. Yes, there are other colors as well, but this particular image doesn't show quite how bright the yellow is. Not so common these days, but mercury streetlights still exist in various parts of the UK, and they have a very bright green plus a little bit of other colors as well. But both sodium and mercury streetlights are being replaced with LEDs because in principle they're cheaper to run. But you can see the problem. They don't just emit at 1 or 2 or 3 characteristic colors. LED streetlights flood our night sky with all of the colors of the rainbow. The entire visible spectrum is produced by LED streetlights. So when we're thinking of how to get rid of streetlights from our images, we have to think about what streetlights we've actually got. And the number of filters that we can buy to try and address this problem is much bigger than I appreciated till I started looking at adverts, and I found more than 50 different filters from 30 different manufacturers. Now, some of these manufacturers might conceivably be buying the same filter and then branding them with their own particular mark. But even so, there's a bewildering number of different filters, and we have to ask ourselves, well, do they all do the same job? What I'm going to do is pick a few of them to demonstrate in the PowerPoint and a smaller number to demonstrate live what those filters do. So what's going to happen in the next few minutes is I'm going to switch on a light source, which hopefully will not blind you too much. It's a relatively bright LED source, but I put it behind a diffuser to diffuse the light and then put it through this slit in a black piece of card. And if we take that effectively line source here, this slit, and look at it through a diffraction grating, we will see a spectrum. And I have provided you with diffraction gratings. Don't use them, yeah, by all means circulate them. What I'm going to do in just a moment is introduce a color filter in front of this slit, and that color filter will change the spectrum that you see in this part of the slit. So notice that when I put the filter in place, notice that the top part of the slit and the bottom part of the slit remain unfiltered. So in other words, there will always be the full spectrum at the bottom and the full spectrum at the top, and I'm going to leave those there because they're a useful reference, if you like, for what do you see when the light is coming through this filter. In other words, what does the middle look like? And so that's what we're now going to do. And so a box of diffraction gratings is now passing amongst you so that you all now all have a diffraction grating. Please take one, and if you wish, take it home so that you can check the spectrum of lights in your house and, more importantly, the lights in your neighborhood, the street lights. So let me kill the PowerPoint, and now we switch to the live demonstration. Okay, so we're done with the live demonstration, so returning to the PowerPoint, I'm now going to recap what I hope you've seen in the last few demonstrations. So the first thing I showed you was a dual band, and when that filter comes in, it reveals that we are seeing only 2 colors, and those colors correspond to hydrogen and oxygen. H alpha is just the label given to one of the particular colors emitted by hydrogen atoms. All atoms have different energy levels, and depending on what those electrons are doing in the energy levels, they will emit different colors. So dual band will be very effective at letting through the light from nebula and killing street lights. Remember, we had that little picture of a nebula, and it was red from hydrogen and cyan from oxygen, and that's precisely what we're seeing here. Then I showed what happens with a tri-band filter. In comes the tri-band filter, and that shows essentially the same thing, except that we now have 2 bands on the right. It looks like one wide band, but it's actually wide enough to encompass hydrogen and another of the hydrogen lines. Hydrogen emits in the red, but it also emits in the blue as well. And so we have hydrogen alpha in the red, and we have oxygen, which is sort of cyany color, and another line of hydrogen called hydrogen beta, which is in the blue at about 500 nanometers or so. So tri-band filters are very good at, again, killing light pollution, but letting through most of the hydrogen from these various nebulae. Quad band filter, Well, there's a limited use to quad band filter. As its name implies, it's now letting through 4 wavelengths of light, which is probably a little difficult to see if this presentation is made in daylight, but actually it's wide enough in the red to encompass another line from a different atom, from sulfur. And although sulfur sounds a bit odd, there are in fact nebulae out there which contain a considerable amount of sulfur as well as hydrogen as well as oxygen. For instance, if you cast your mind to the Hubble picture of the pillars of creation, that's a picture in which you're looking at the hydrogen, the oxygen, and the sulfur in that particular cloud. But the problem is sulfur and hydrogen alpha are actually very close together. So if you take a picture with a color camera using this filter, sulfur and hydrogen will both look red. So you can't really tell them apart. So you get a little more light from the nebula, but you can't distinguish where the sulfur is from where the hydrogen is. So I would argue that that one is of more limited use. But I found a number of other filters from some of my friends who bought filters for various purposes. So we had a root through and we picked out a few. Thousand Oaks is just the name of a particular brand of filter. And it didn't say on it what type of filter it was. So I put that in to the slit and took a picture of it through a diffraction grating, and it turned out that it looks like that. In other words, it is actually a tri-band filter. It might not say that on the filter, but it's still letting through hydrogen, oxygen, and hydrogen beta as well. Why they don't label it as a tri-band filter, I don't know. Different manufacturers have different ways of selling their products. Common filters are often labeled UHC. This means ultra high contrast, which doesn't mean anything in itself, but it's basically saying if you use this filter, you will get better contrast between the nebula and the sky. In other words, it'll darken the sky and make the nebula easier to see. Some people sell these filters saying it will make the nebula brighter. It never makes the nebula brighter because it's a filter, but it will make the sky darker and it will make the nebula easy to see. So ultra-high contrast simply means you'll get better contrast and hopefully improve the visibility and make it easier to photograph these various objects. And if we look at what it does, this particular UHC filter lets through the oxygen and apparently nothing else. It's not just a little bit dark. I don't think there's any hydrogen coming through. So this particular filter actually is only any good if the object that you're photographing is emitting lots of oxygen light. As long as there's lots of oxygen in this nebula, it'll do a good job. But if your nebula is mainly hydrogen, this is going to show you next to nothing. There's another type of filter called a CLS filter, and CLS stands for City Light Suppression. In other words, if you have very bad light pollution, because you're living in a city rather than living in a rural area, these filters supposedly make life easier for you. And if we look at what they transmit, notice that it's not just a small band, it's quite a range of reds and quite a range of greens and blues and purples. So again, it covers all of the interesting elements of the nebula, sulfur and hydrogen and oxygen and hydrogen beta, but notice that it's taken out quite a wide range in between the reds and the greens. And that tends to be, that little desert there, that dark area, that tends to be where streetlights are. So it should do a good job of taking out streetlights. Other filters, they might just be called contrast boosters, which again means nothing until you actually look at the spectrum and then you find out what they actually do. Again, it's letting through most of the light. It seems to be killing the violet end of the spectrum, but most importantly, it's a large black area around the yellow, which is where you would expect sodium streetlights to be at their brightest. Notice there's also some darker regions where you would expect mercury to be shining. There, the mercury shining in the green, sodium very bright in the yellow. So this particular filter would be very effective at removing sodium street lighting, but would be not quite so good if you have mercury, because it only dims the mercury by 10 or 20%. It doesn't bring it down to 0. So again, useful providing you understand which particular streetlight pollution that you have. And finally, this one that I described as a light pollution filter from the well-known manufacturer Hoyer. They sell it more as a starscape filter in the sense of if you want to take a nightscape, a night sky with perhaps some objects in the foreground, whether it be some interesting landscape or mountains or buildings, then again, they sell it as a way of reducing light pollution. But when you see the effect, again, it's only really the sodium that it has an effect on. If people buy this thing as a light pollution filter, thinking that it will reduce pollution from LED streetlights, they're wrong. It won't. It will only ever be effective against sodium streetlights. So I do wonder whether or not people are mis-selling some of these filters because they're not being absolutely clear this will not work effectively with new LED streetlights. So there's a summary of all the spectra I've shown. There's no filter at the top, no filter at the bottom, and all the others back to back, as it were. So all of these filters try to transmit as much as possible, definitely oxygen, probably also hydrogen, and they might then transmit other lines such as hydrogen beta or sulfur. But one thing they do all have in common is they try and reduce as much as possible the emission coming from where most streetlights are emitting, sodium in the yellow, mercury in the green, but not doing much for LED streetlights. If we come back to this rather confusing spreadsheet of all the filters I could find, it really doesn't help the fact that every manufacturer has a different way of describing all of these filters. So some might use the acronym CLS, City Light Suppression, fine. Some might use the acronym UHC, Ultra High Contrast. But if we pick out UHC, for instance, different manufacturers use that acronym to mean different things. For some manufacturers, UHC means a dual band that lets through hydrogen and oxygen and kills everything else. But for other manufacturers, it's a tri-band filter. And for other manufacturers, it's one that lets through quite a range of different colors and kills a few colors around yellow. For other manufacturers, it only kills yellow and doesn't kill anything else. So you can understand confusion reigns if somebody asks, which light pollution filter should I buy, even if they look at the descriptions from manufacturers. It really doesn't help unless you happen to have a physical copy of the filter and a diffraction grating, or if the manufacturer actually shows you the transmission of the filter, only then can you actually tell what the filter does. So the bottom line is, if you're looking to photograph stars and galaxies, which remember emit across the whole spectrum, or if you're trying to photograph nebulae, which emit only at very specific colors, then if you have sodium streetlights, or whether you have LED streetlights, and remember sodium emits mainly in the yellow, LED emit across the whole range of the visible spectrum. If you buy yourself a light pollution filter which is supposedly going to work for sodium streetlights, then generally speaking it will do a good job with sodium streetlights. But it will be next to useless with LED streetlights. It'll reduce the yellow, but 90-something% of the light will still get through in the other colors. If you go for a dual band or tri-band or quad band filters that let through explicitly hydrogen and oxygen, then any filter like that will do a good job on nebulae. But what about broadband sources such as stars and galaxies? Well, you're only letting through a little bit of red and a little bit of cyan. So if your stars are emitting at all wavelengths, then you're going to be reducing the amount of light coming from those stars or galaxies. So yes, it will actually reduce the sodium street lights, but it will reduce the starlight as well. So effectively, you're not gaining any signal to noise. You are effectively reducing the noise and reducing the signal, so you're no better off. So there's no point in using these particular filters that are designed to work well with nebulae. There's no point in using them on stars and galaxies if that's your preferred target. So in summary, if you're trying to look at nebulae, or if you're under sodium streetlights, there will always be an option available to you, and some filters will work better than others. But this top right box, the elephant in the room, is if your source of light that you're interested in is the whole spectrum, and your interference from streetlights is the whole spectrum, there's pretty much nothing you can do about it. No amount of filtering is going to help you. Doesn't matter what the filter is. The only solution you have to try and make nice pictures in astrophotography, if you have LED streetlights and you're after natural light, stars and galaxies, the only solution is software processing. Luckily, software is quite good at dealing with a certain amount of background. It's rather difficult if you're in the middle of a city, but as long as the streetlights aren't too bright, software does a great job. And as a sort of spin-off, if you do use tri-band filters or something like that, as well as allowing you to see the nebula and basically the stars not so bright, it can also reduce the glow from a moon, so you can take pictures under moonlight when normally the sky is too bright to use. And again, you can take pictures even in twilight when the sky is still blue, when you think it might not be dark enough to take pictures. But also it has the advantage that because light from stars is broadband across the whole spectrum, if you use a tri-band filter, it makes the stars a bit darker. Now that might seem a bit odd to say. Why on earth would you take pictures of the night sky and try and make the stars darker? But if the target you want is the nebula, then sometimes there are so many stars in your image, they tend to crowd out and make it difficult to see the nebula. And I can show that in an example. This is a picture of the Andromeda Galaxy. It's a broadband source, and this was taken with no filter because there is absolutely no advantage to using a filter for a broadband source like this. There's no point in limiting the light coming from something which is emitting at all wavelengths. You may as well pick up all wavelengths. There's not a huge amount of color there, but basically no filter is fine. But for this particular object, it's actually a supernova remnant. It's a nebula, which is the result of a star going bang 10,000 years ago or so, and basically some star in the middle there has gone bang, and this is, if you like, the shock wave of the bubble that was produced and has been expanding ever since. I took this picture back in 2019 from a dark sky site, from a star party way away from light pollution. This was the best I could do, and there's an awful lot of stars which are making it difficult to see some of the detail in the nebula. But then I took it again in 2022 with this filter to try and not only limit the amount of light pollution, because I took it not from a dark sky site, but from my front garden. I took it with a tri-band filter. It not only reduced the pollution, it also meant that the stars were a little dimmer, and hence it's easier to see the structure in the nebula. So this was actually close to an LED street light. I now have LEDs, have had for a few years now in my street. And this particular picture was taken less than 10 meters from a street light. So this street light was quite definitely lighting up the sky above me. And yet, with a tri-band filter, because it's suppressed the sky glow and it's made the stars a little dimmer, they are not dominating the picture. Now we can actually see the wood for the trees. We can separate the wheat from the chaff. Can I think of any more cliches? Not at the moment. So we can definitely start to see detail that's in the original image, probably, but it's just so difficult to see it because there were just too many stars. And even software has a job trying to separate out the structure of a nebula from the stars if there are too many stars. There literally are just so many of them. If I make this a little bit bigger, what you would see of that nebula, if you look through a telescope and try to see the nebula, that's about what you would expect to see. You can just about see very faint arcs of nebulosity. But by using a tri-band filter and playing around with software, we have the ability to say, right, I can now effectively separate out the nebula from the stars, and I can arbitrarily say, well, I'd like the nebula to be a little bit brighter, so I'll just make it a little bit bright. No, I think a bit more. No, I think a bit more. And it might be taking it one step too far, but with software these days, as long as the star field is not too crowded, as long as the stars aren't too bright, you can effectively ask the software just to remove the stars. And then you get, perhaps it doesn't show too well in a brightened room, but there is an enormous amount of structure even in the faint parts of the nebulosity as well as in the bright parts of the shock wave of this particular supernova. So tri-band imaging is fantastic if you can't find your way to a nice dark sky site, and it doesn't rely on very sophisticated software processing to give you very nice images of objects such as this Veil Nebula supernova remnant. That's it. Thank you for listening.